Hello physics students. So in the last couple videos you learned Faraday's law, which says that a changing magnetic flux creates a voltage in a coil. In this video you're going to see another example of how we can change the magnetic flux to induce a voltage, a current, and today we're going to also see a force on a coil as long as part of that coil or all of that coil moves in the presence of a magnetic field. So, induction and forces. So the first case, what we have is two rails like this connected with a wire and a resistor, and then we've got this bar that's sliding across the rails like this. Now what this does is it creates a changing flux in the loop that is right here, this rectangle, because when this bar ends up over here, now we've got more area with the same magnetic field, so we have more flux, BA cos theta. So first thing that we're going to do is determine the direction of the current that would be induced in this bar. So I'm going to create a little pause to allow you to practice Lenz's law to determine the direction of the current in that bar. So go ahead and give it a shot. Okay, so this is what you should have done. You should have said, okay, we're gaining flux into the board. So that means that B induced has to oppose that. In other words, it has to be out of the board. And that means that if you use the right-hand rule between current and magnetic field, you see that in order for the B induced to be coming out of the board like this, we need a current to go from the bottom of the board to the top of the board. In other words, up in this bar. So this is the current induced in the bar. All right. So as long as this rail slides, this will produce current. By the way, I believe this is the way that the arms at a railroad track, the indicators, how they can tell a train is approaching, come down and have the lights come on, is that when a train approaches the intersection, what happens is it induces a current in the, or voltage and a current in the rails and the axle of the train, because the Earth's magnetic field in New York has a magnetic field, not only does it point north, but also has a component that points into the Earth. And so when the train goes either towards the intersection or away, there will be a current induced in the rails. All right, so there's that example. The second way you can make voltage and current with a moving coil is if you have a magnetic field, a region of magnetic field, and then you have a coil that moves into or out of that region. So this coil has dimensions of length, width, and it's moving with a velocity. Now before that coil enters into the magnetic field region, then there's no flux, and the flux is not changing either. So there will be no voltage induced, no current induced. But as soon as the coil starts going into this magnetic field region, there is now a changing flux, because as you can see from this dotted line, the area that has magnetic field in it is right here. But as the coil continues to move in, that area is going to be increasing. So if the magnetic field's constant but the area is increasing, flux, being BA cos theta, will be increasing because of the increasing area. Furthermore, we can determine the direction of the current in that loop. So what I want you to do, I'll create a little pause, and what I want you to do is to figure out whether the current goes clockwise or counterclockwise. Again, don't be a spectator, give it a try. So go ahead and do that now. Figure out the current in that loop. All right, here's what you should have done. You should have said, okay, we've got more and more magnetic flux going into the board, because as this goes in this way, it's going to capture more of that magnetic field inside the loop. So that means to oppose that, we've got to have B induced coming out of the board. I'll just put BI maybe for induced, because it's kind of tight there. Now we use this right-hand rule again, and so we put our four fingers in the direction of the magnetic field coming out of the center of the loop, and we see that our thumb goes this way. So once again, the current goes up like this, the I induced. Now, so there's current here while the loop is coming in. But then what happens, once the loop gets fully in the magnetic field, there's no more current induced because there's no changing flux. As I'm coming here and capturing more magnetic field as this part of the coil moves forward, this part of the coil moves forward also and it loses magnetic flux. So this part's gaining flux, this part's ensuring a loss of flux. Overall, we have the same B, the same area, and the same angle, so BA cos theta doesn't change, no changing flux, no current, no voltage, no current. Then once the coil starts coming out of the magnetic field region, once again, we have changing flux because we have changing area. The only part of the coil that has magnetic flux through it is this part. And then as this back end of the coil moves forward, we're going to have less and less of that flux. So there is a changing flux, therefore there's a voltage induced, therefore there's a current induced. So what I want you to do is go ahead and practice Lenz's law again to figure out whether the current here goes clockwise or counterclockwise. So go ahead and do that now. All right, what you should have done is this. You should have said, we're losing magnetic field going into the board. That means B induced has to go into the board as well because we're losing this. So B induced has to try and prevent that from happening. Has to try and prevent the change. So I put BI for B induced. Yeah. And now to figure out the direction of the current, I use this right-hand rule again. Point my four fingers into the center of the loop for the magnetic field induced, and you see the current induced on the bottom here goes this way backwards, so it goes clockwise this time. And what I'm going to do is I'm going to put the current here going up like this, and there is the I induced. In other words, we have I while the loop is on its way out of the magnetic field region. Once it gets completely out of the magnetic field region, the flux is zero and it remains zero. So there's no changing flux, no voltage induced, no current induced. So there's only current induced while the loop is on its way in and while it's on the way out. But before it gets in, when it's completely in, when it's completely out, no current induced. So motion creating induced current. What I'm going to do is create a pause now to give you a chance to copy these diagrams down to the best of your ability. All right, so now what we want to do, of course, is not just figure out that current is induced and which direction it's in, but we also want to figure out the amount of current. So the first thing we're going to do is figure out the voltage. Now the flux, in order to find the voltage, we first have to find the flux. The flux is B times area times cos of, and then the cos will just be 1. So I just put B times area. That's the flux. Now the area is the area of this rectangle, length times coordinate x as this bar slides along. Or you could say length times the coordinate x, how big this portion of the area is when the loop is on its way in or out, the x from here to here, for example. So that's the flux in both cases. Now, to get the voltage, I put absolute values. I'm going to leave the minus off. I just want to know the magnitude of the voltage. I have to take the derivative of the flux with respect to time, and so the flux is BLX. So B is constant. The length here is constant, the the distance between the rails or the size of this loop here. So the only thing we can take the derivative applies to is the coordinate x. dx dt, of course, is velocity. So that is the voltage induced in a coil with movement involved. BL times the speed at which the coil is going in or out of the magnetic field region, or the speed at which this bar is sliding. Now, I also want to point out it's important in this coil here that you understand It's the length of the coil that's cutting into the magnetic field, not this. This coil could be 1 meter or 10 centimeters. It doesn't matter how long it is this way. What matters is the length this way that's going into the magnetic field there. Okay? Of course, if it's longer this way, that means there'll be more current being induced as it's going in because it takes a longer time for it to get fully in or out of the magnetic field. But the amount of voltage only depends on that size. Next, we want to determine the current. So we just use Ohm's law, V over R. Now, we have a resistor in that coil, but there's no resistor here. But as you remember, wire itself has resistance. So it'd just be the resistance of the coil. Plug in BLV for voltage and resistance, and there's the current in the coil. All right, let me create a pause to allow you to copy these notes down. All right, next we're going to calculate the force for this bar and for these loops, because there is a force. The reason there's a force is because we have a current inside of a magnetic field. So in order to determine the direction of the force, we've got to use our right-hand rule. Not this one. This one's current direction of magnetic field. This one is velocity or current, magnetic field, force on a positive charge, or force on a current. So in order to figure out the force on this bar, we would put our index finger toward the top of the screen for the direction of the current. Now these three fingers have to align with the magnetic field. While I keep this index finger constant, you know what? I just remembered. I should allow you to figure that out, give you a chance. So I'm going to create a pause, figure out the direction of the force on that bar. All right, well, I gave you some hints, but current, then these three fingers have to go in the direction of magnetic field. So what I have to do is turn my wrist like this, and now current, magnetic field, and my thumb points backwards. So maybe I'll do a different color, just why not? And we'll do it for these also. Well, it's the same thing. We got current, magnetic field, thumb backwards, so this feels the force backwards. And same thing here, current, magnetic field, thumb backwards. So maybe I'll put it here. By the way, I didn't need to do that. I know it has to be backwards from just energy conservation. When there's current, there's going to be heat produced. So there's energy, heat energy that's appearing. What I know is that if heat energy is appearing, some other kind of energy has to be disappearing because energy is conserved. You can gain one kind of energy as long as you lose another. And so what that heat energy is coming from is the kinetic energy loss of this bar or the kinetic energy loss of this wire loop. If the force was in the forward direction, we'd be gaining heat energy and kinetic energy. What we could do is then put a rail like this, give it a little tap, heat would produce, and the bar would accelerate and go faster and faster, producing more and more heat. That would be the answer to the world's energy problems. Things would be accelerating while we're gaining more heat energy. Hey, now free energy. Can't happen. You gain heat energy, you got to lose some other kind of energy, kinetic energy. The force has to be backwards. All right, anyway, so let's go now and calculate the magnitude of that force. So force on a current for a certain wire is ILB sine theta. Now the current we already derived over here, so we're just going to plug that in for I. We got LB. Now the angle is between the magnetic field and the current. The magnetic field and the current, which is 90 degrees in all cases. So here's the expression for the magnetic force. Finally, let's calculate the power, because if heat is being produced here, or in this wire material in the conductor, that's power, heat in a certain amount of time. Just like energy's got to be conserved, then in a certain amount of time, the energy conserved means that there's power being conserved also. So the power is either the heat produced in the resistor, or the mechanical power of something pushing this to keep it moving and not decelerating. So either way, if you figure out the power, the mechanical power pushed to keep this thing moving at this constant velocity, you could use force times speed. And here's the force times speed and the expression for the power. So another way you could figure out the power is not the mechanical power you're putting in, but the power of the heat produced. You could do I squared R or V squared over R or IV in this resistor, and in the end, the circuit power would come out to the same exact expression again, because energy is conserved. You're putting in power mechanically, it comes out as heat power in the resistor. All right, so let me create a pause to give you a chance to copy these notes down if you need a moment to catch up. All right, so that's today's video. Motion of a coil in a magnetic field producing voltage, producing current, producing a magnetic force in the backwards direction, and then producing either power, heat energy in the resistor, or mechanical power to keep this thing from slowing down, moving at a constant velocity. So that's it for today. I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next video.